So the lecture is on ARM TrustZone and an application of the ARM TrustZone technology to regulate smart devices. Okay, so the motivation for this work is that these days we find devices everywhere. Smart watches, smart glasses, including even things like smart contact lenses, right? So there are real applications of things like smart contact lenses where they are obviously they are placed within the eye, and Google was investigating it for a while, not to deliver advertisements directly to your eye, obviously, but actually the smart contact lens is in touch with your eye, therefore is also in touch with the tears that your eye continuously produces, and just by measuring things like the salt level and the sugar level in your tears, it's able to tell you if you have some health problems. So it's continuously monitoring you. And obviously smartwatches, I don't have to tell you about the benefits. A lot of you possess one of these devices. It continuously monitors things like your heart rate and so on. And given this day and age, it also monitors things like SpO2, which we know is like so important to monitor in this day and age of COVID. So these devices are extremely becoming extremely pervasive. All of them are using ARM-based technology. For whatever reason, ARM-based chips became extremely popular in this embedded sector, um, primarily because of, I think, better power characteristics that they are being adopted here. Of course, there are smartphones, but also things like home-based appliances are smart nowadays, and cars, and also drones, right? These are all devices around us that are becoming more and more pervasive. So the number of devices is kind of increasing at an exponential rate, and you can see that these slides are slightly old, but there are the predictions nevertheless stand. um, so 1.2 billion new smartphones by 2018. I think that number was met. And the most important trend is, of course, that of 50% year per year increase in the number of devices used in this enterprise sector. Um, so that number is like extremely shocking in terms of the number of proliferation of these devices. Okay, and this is slightly dated. Obviously, we are now past iPhone X, but it shows you a kind of important trend in how the device capability has increased in terms of the number of peripherals, in terms of the resolution of things like cameras, resolution of the screen, the number of CPUs available, and the reducing, uh, and sort of like the increasing reliance of humankind on these devices. So the very first iPhone, just one CPU, uh, you can see that the screen resolution was pretty low, camera was pretty low, and every generation of the iPhone has added a new sensor. Okay. So initially it was light, accelerometer, proximity, you added compass, you added gyroscope, infrared, added fingerprint, added barometer. Now there is so many more, right? Touch-based sensing, and there are like cameras that continuously monitor your facial expressions, and they are able to track your eye gaze. So technology continuously improves, and the devices are becoming increasingly capable. Now, generally, this is perceived as a good thing, right? I mean, devices, this is why you flock to buy the new device as soon as it is released. But the what the paper and the theme of today's class is going to be is that these devices can also be misused, right? These increasing capabilities can also be put to bad uses. Okay, so devices can be misused in a number of ways, right? I mean, you can think about malicious end users who leverage these sensors to exfiltrate or infiltrate unauthorized data. And you can also think about malicious applications on these devices that can achieve similar goals, even if the end user is not overtly malicious. So I'll give you some use cases to convince you that this is a real problem. Um, okay, so the very first use case is that imagine you're going to a government office, or a corporate office. The problem is that there are a lot of sensitive documents that or meetings that you might be party to or privy to, right? You might be an employee of a corporate office, and you walk into a, let's say, boardroom meeting with your phone in your pocket. Um, what is the guarantee that you're not recording the contents of these meetings and then probably later on uploading it, or maybe broadcasting it uh, directly over the internet, right? With 3G, 4G being available, you can directly do it directly from the boardroom. So the camera and the microphone obviously can be misused. And not just that, even if you say, look, camera and microphone should be off, you can store things on local media and you can actually broadcast it out later. So today the solution, especially if you go to a high security government facility or if you go to certain companies, right, it is that of physical security scans and device isolation. Okay, so this is just a picture over here that is kind of an overdo of it, but essentially you're asked to keep your device in what is called a Faraday cage. So Faraday cage is nothing but a wire mesh like this, which prevents electromagnetic radiation from going in or out. Um, and what this does is that if you keep your phone in a Faraday cage, it cannot communicate directly with the cell tower at that point. In fact, all of you have a Faraday cage in your house right now. Do you know what it is? Any ideas?
Microwave?
Yeah, your microwave, right? This is why your microwave is able to cook your food without cooking you. There is a wire mesh structure in your microwave that prevents the microwave radiation from leaking out of the box, that metal box from which you're cooking your food. In fact, cars are also Faraday cages. This is why when there's a lightning storm, it is best to stay inside your car, because the lightning, if it strikes the outside surface of the car and you are protected inside. Okay, so the real application of this, of course, it's not just government or corporate office. These days phones are used as payment devices, right? I mean, you've got things like magnetic stripe technology, near field communication, NFC, and so on, that are used for pairing up with your phone. And sometimes, even like there is a advertisements, you tap your phone twice and then the payment is authorized, right? How is this? It is because there is a point of sale device that pairs with your phone and is able to authorize the money transfer. Of course, there are other methods of authentication. Perhaps you're asked to enter a PIN, or maybe there's a second factor authentication. But let's say there's a vulnerability, and your phone is able to directly pair with this with the malicious point of sale device. Your phone can be the point of sale device can actually pair with your phone, get queries of how much balance there is, or even transfer money. Okay, so this is why you see this picture over here. There are wallets like this being available where you can put your phone inside the wallet. The wallet is actually a wire mesh. There's a wire mesh inside, which is a Faraday cage that prevents your phone from pairing with unwanted devices on the outside and communicating with them. Okay, so this is a real concern, right? And in fact, if you go to many offices and so on, you're supposed to keep your phone outside and then go in. I'm not kidding you. Because this lecture is recorded, I will not name the company, but there is a very famous mobile phone manufacturer, extremely famous, home name. But employees of that company, when they go, especially visitors and so on, even employees, when they go to the headquarters of that company, they are at the security gate. There is a guard who places a tamper-proof tape on the camera. Okay, the reason is because when they go in, they don't trust the employees not to record pictures of, let's say, the next generation models that are coming out. The point is that if they record that and by mistake, if they post it or if they maliciously post it, it's a big hit for that mobile phone manufacturer. So the tamper-proof tape is put on the camera, and the point is that when you're going out, the security guard will check that tamper-proof tape is there. If you ever try to remove it, of course, there'll be signs that you try to remove it, and immediately the report is filed with your manager, first line manager, saying, this attempt has happened to remove it, and it is as serious as that. If the second time it happens, your employment is terminated on the spot. Okay, you can ask around. And you will probably figure out the name of this company. I will not name it because it's a recorded lecture, but it's as serious as that. Companies take their privacy as important, as seriously as this in this day of pervasive mobile phones. Okay, so that's one setting, and this is becoming important because of this trend of bring your own device, where more and more employees are beginning to bring their own devices into enterprise settings. And the problem is that when the employees bring their own devices, you can't just ask them to shut the peripherals down arbitrarily, right? Because the peripherals might actually be used for work. You can't just shut down the camera because maybe at work you have to take like a video call, right? Then what do you do, right? So it is not as easy as just saying, okay, I'll put a tamper-proof tape and thing is done. It might not even be video call. It might actually be face-based authentication for opening doors in offices and so on. It might recognize you and then let you in. And this is a solution for which you cannot just say, "Hey, I'm going to turn off the camera on my mobile phone." Okay. Second, of course, is classroom and exam setting, right? And you're all familiar with this. I don't know what the restrictions in GATE exam centers are, but a few years ago there was this article about students going in full sleeve shirts to the JEE exam center. They were asked to remove the full sleeve shirts, and there were reports that they exchanged their shirts with their fathers, more half sleeve shirt and so on, so that the examiners can check that you don't have hidden devices on you. I don't know what's the deal with GATE. Maybe you guys can tell me what's the security measure when you go into an examination testing center. What do you have to do? Do you have to keep your phone outside? What can anybody chime in? What is the latest and greatest?
Sir, if we talk about the phones are not allowed in the exam hall. They generally discourage bringing phones to the center. They say we take no responsibility.
What about smartwatch?
I don't think there is any explicit checking, but it's not allowed. But when I took the paper, nobody checked it, like what kind of watch I was wearing.
I'll tell you an attack right now. It's on the screen, but I'll tell you about it right now. So
maybe others can say because I had that experience.
Okay. Did anybody else, like you were wearing smartwatch, were asked to remove it? Was this there?
Yes.
Sir, in my center,
Yes,
we weren't
all
even
in my
allowed to
center.
take water bottles inside.
Oh, no water bottles also, huh? Okay.
Yes, sir.
This is the TCS testing centers, right?
Yes,
Yes, sir.
ION digital zones.
ION, yes. Oh, I see. And they will give water if required.
Not really, sir, but yeah, I suppose.
Okay.
In my center, there was a water cooler, and we were allowed to go to that. We are not allowed to take the bottle, but we were allowed to one by one person per room.
This is you guys are actually giving me more and more useful information to sell this work, because supposing what happens if like a student actually is hard of hearing and is wearing a hearing aid, what happens to that student? They're asked to remove the hearing aid? I don't know, because obviously these our testing centers and our institutes are extremely cognizant of people with that are differently abled. So hearing aids are obviously a very important thing for people who can't hear. But there are people who will misuse that, right? What is the guarantee that somebody will claim they cannot hear, wear a hearing aid, and then there is somebody standing outside telling answers? These days, all hearing aids are Bluetooth enabled. Okay, what prevents that? And smart glasses, right? Today, all of you wear glasses of regular kind. Few years ago, there was a very famous project called Google Glass. It got scrapped, but it's a project way ahead of its time. Imagine somebody comes in wearing a smart glass. Now, what's the solution? They're asked to keep the smart glass outside. Maybe that person really cannot see. Then what happens? Right? Anyway, so these are all challenges, right? You can see that these challenges are going to become more and more real in the near future. You can't just say, "Hey, remove your glass," because maybe that person really cannot see without the glass. Okay, so here is a very interesting attack. This was published in 2014, but you can see it's kind of a very future-looking attack. So imagine you have a smart watch, and it's showing the digits in this LED format, right? This typical old calculator style. Now, GATE is an objective style exam, right? So maybe you and your friend who are taking the test at the same time decide on a protocol, right? Maybe you will communicate the question number and the answer number by turning on or off individual LEDs in the thing that's showing the time, right? Maybe you'll turn off this LED and turn this on and turn this off. And as long as you know how to read binary properly, that will be like 010 that tells you that is question number, question number 2. Okay. So, and then, there are obviously only 4 choices for the answer, and then you can communicate that also in binary format. And as far as the examiner is concerned, right, you and your friend pair your Bluetooth watches and you're able to communicate via this medium. And as far as the examiner or the person in the TCS ION center is concerned, or the CCTV camera that's monitoring you, you're just checking your time or fiddling with your watch. Well, if you're fiddling with your watch, that's your problem, right? I mean, why should they prevent you? But actually, what you're doing is communicating answers. And this is possible, right? I mean, this is possible because the devices can communicate via Bluetooth. And where are you checking this, right? Of course, if you're asked to remove the watch, that's a very low-tech solution, right? That's like saying, hey, remove the hearing aid, remove the glass. And the point is that these are not future-proof solutions. I don't know what is going to happen in the future as more and more of these devices come. In particular, maybe you're wearing a smart contact lens and your friend is directly beaming the answer into your eye from the outside. And who is to say, remove the smart contact lens when you're coming inside? How can they even check that you've got a smart contact lens in the first place? Right? I mean, are they going to open your eye and see? I don't know. Right? I mean, so things like keeping the water bottle outside, it might work today. And these are arbitrary decisions. As you can see, it's inconsistently even applied. Right? One person was not asked to even bring water bottles inside. Another person had a different experience. So these are all based on the whim and fancy of individual testing centers. No consistent rules are there. Okay, so you can see, right? I mean, like low-tech solutions for high-tech problems. Okay, so the current solution, of course, is deterrence via rules and threats, right? Like the things that you guys faced, and probably invigilation to ensure compliance. Right? Somebody walks around, there's a CCTV, they check, okay, are you following the rules? But it's a problem, right? It's a problem because of things like assistive devices that are becoming more and more pervasive. And of course, the people who really need to use these devices must use them. But what is to prevent another person from claiming that they are differently abled and misusing these things, right? There is nothing that prevents this today. Okay, and other social settings, right? I mean, like there are also problems there, right? When Google Glass initially came, a number of people were very afraid that people walking around wearing this Google Glass are recording things. So you go to like some the bathroom or something and then turn it on. Obviously, the other people there are concerned about their privacy. And of course, the informal enforcement here was that many restaurants said, hey, when you're coming inside, don't wear this glass. And obviously then people who are wearing this glass will stop going to that restaurant. Okay, so those are benign cases that can be misused. Of course, there are also malicious applications that can exploit the sensors. More and more applications use these sensors in all sorts of novel ways. So here is my favorite example. This is from 10 years ago. And the attack, if somebody were to do it again today, would only be a more effective version of the attack that was demonstrated. And so the attack over here works like this, right? So many of us, what is our habit when we come to work? We keep the mobile phone, we take it out of our bag or pocket, we keep it on the table, and then we sort of type our passwords and log into our machine. And then, we do whatever, check email, browse, whatever it is, right? But probably the phone is kept right next to your keyboard, and then you're doing your activities on your keyboard. There is no direct physical connection between your phone and the keyboard. But the point is that your phone has an accelerometer, gyrometer, and so on, gyroscope and so on, that are actually measuring things like movement of the phone, the tilt of the phone, and so on, right? And they can recognize vibrations. That's how they are able to give you portrait or landscape mode, right? Based upon where the phone is. Now, the point is that these peripherals like the accelerometer, the gyroscope, they have become so sensitive over the years that, in fact, if you type on your keyboard with the phone next to it, the vibrations that are generated from when you press the key on your keyboard are transmitted from the table to your phone, and those vibrations are actually perceptible on the phone. Okay, if you have an app that can look at the accelerometer, can actually go and sense those vibrations. They're tiny vibrations, but so the phone can sense it. Now the point is that if you press A over here, right, that's probably going to be stronger for vibration because it has to travel a shorter distance to the phone than if you press, let's say, Enter or L or something like that. It'll be a weaker vibration. Now, just by measuring the strength of the vibrations and doing like a frequency analysis, A is more common than things like Q, right? Some machine learning model over the pattern of vibrations observed, the phone can actually infer what you're typing. Okay, and they found in 2011 that around 80% accuracy for word recovery. Now imagine, you're typing your password over here on your keyboard. Your phone, without actual physical connection to the keyboard, is able to infer your password. That's scary, no? And that is happening because the accelerometer is actually being used, and typically you don't even get a permission screen for accelerometer access. Any app can access the accelerometer data. You don't even need permissions from the permission screen for that. Okay, and this actually gets scarier and scarier. People have demonstrated attacks using every sort of imaginable sensor on your phone. And the odd thing is that the accuracy improves with each generation of devices and sensors. You know what attack really took me by surprise most recently? So your phone has a small motor that vibrates, right? Whenever a call is received, you can actually configure it. That's the vibration mode of your phone. Now, how does that work? Well, there's a small motor, or not motor, but rather a small, piece of iron weight that goes back and forth based upon electromagnetic signals that are delivered to it. Right? That's how it works. So you give the electromagnetic signal, and then the magnetic field that's generated causes this little iron weight to move back and forth, and that's how the vibration is generated, and that's how your phone works in vibrate mode. But the attack that I read about, this was I think 2 years ago, works like this. So when that there is a duality between motors and dynamos, right? So a motor is something where you give an electromagnetic field and then the mechanical motion is produced. What's a dynamo? A dynamo is you take mechanical motion and then you produce electromagnetic field, right? So exactly the same duality applies over here. When you speak, apparently the pressure waves from your acoustic, the waves that come from your from the throat, they cause tiny movement in this little iron weight that is sitting in your phone, and that little iron weight, as it moves because of these acoustic signals, can in turn generate electric current in this vibration thingy. That if you have access to, let's say, an app that can infers these electrical signals, you can actually determine who is speaking and what they are speaking in the room, even if your microphone is turned off, right? So the vibration device on your phone is being turned into a microphone. Can you imagine that, right? I mean, that's absolutely mind-blowing. So that phone in your pocket, I hope you never think about it in the same way, because it can be used as a spying device in all sorts of really, really out-of-the-box ways. Okay, so that's the point, right? I mean, this attack accuracy will improve with every generation of devices and sensors. And so the claim is that as these smart devices become integrated with our daily lives, ad hoc solutions like banning device use are no longer going to be acceptable. There is another example that I would like to state over here, and this is kind of related to some ongoing work in our lab, which is that that drones are becoming more and more popular, right? I mean, you can buy end-user drones today, and you don't even need a permit to fly your small drone. In fact, you go to every marriage hall, they have a drone that's sort of recording the ceremony. And these drones as you can guess, are equipped with camera and also even a microphone you can put there, and obviously they can be used to record everything. Um, Now, this is a real nuisance, right? I mean, our own defense facilities over here, if you go to like the Air Force facility over here in Jalahalli, right? It's surrounded by marriage halls. And apparently, it's becoming a nuisance over there. They don't like to be recorded. They don't like the inside of the Air Force field over there to be recorded. Who knows what these people are recording, right? So obviously, these armed forces are sensitive about their privacy, but these marriage halls, these people who are recording the marriage ceremony, apparently they take these drones and then they turn them around and then record what's going on inside the Air Force facility. They don't like that one bit, right? Now, it's a real concern. And, those are nuisance drones at least, but you think about delivery drones, right? Amazon is thinking about delivery drones. Zomato, Swiggy, all of these companies are thinking about delivery drones, at least for last mile delivery, right? So this is the situation where the drone comes and delivers food to your house or your products to your house rather than a person coming in. It's actually safer in many ways if you think about it, right? Contactless delivery in the time of COVID. It's awesome. In fact, it is better than delivery because you don't have to stay at home. Maybe your phone can pair with a drone, and even if you're not at home, you're riding a bike somewhere, right? And the bike's GPS sort of pairs with the drone and then tells, hey, you're riding a bike, and the drone comes and lands on your bike, gives your product. You don't even have to worry about missing the product delivery. These are all things of the future, but they're realistic things of the future, right? Now imagine these delivery drones. They're equipped with cameras. Imagine, they can be used to violate your privacy, right? They can follow you around, they can record your privacy, and they can record your location, they can record your faces, and thereby violate your privacy. What do you do in such cases, right? So the point is that you need some sort of methods. You need to evolve some both regulation in terms of policy as well as the mechanisms to regulate these devices to ensure that they are used responsibly. Okay, I'm only going to talk about overt device use. I'm not going to talk about covert device use. What that means is that, supposing you want to go to an exam facility and you want to use your smart glass, right? I mean, you tell the examiner, look, I can't see without the smart glass. I want to use it, but please ensure that as I'm using it in accordance with your rules. Maybe you will say that, look, no internet access, no 3G, 4G access. As long as you conform to that, you can sit inside my classroom, wear your smart glass, and then do whatever you want to, right? Maybe that's the classroom policy, and you're agreeable to that. And that's a better solution than asking you to keep the glass outside and then coming in which case you can't even see, right? So that's covert use. And that's all I'm going to be talking about today. At least it's a step forward. Now, covert use is much harder, right? I mean, this could be maybe you stitch like a 4G device inside into your shirt and then go into the exam hall and then you talk to your friend standing outside. That is certainly possible, and I don't know how to even prevent that. Maybe you're asked to remove your shirt, but hey, maybe you can swallow a pill with a 4G device. Then what do you do, right? I don't yet know how to solve the covert use case, but the overt use case, at least it's a step forward. So that's all I'm going to talk about today. Okay, so what solutions exist today? At least in the corporate setting, there are mobile device management solutions such as Samsung Knox. And the way these work is that, when you go into, so they will, of course, ask you to install this solution on the phone. So as long as you have this device on the phone, this mobile device management solution on the phone, when you check in, let's say, into your corporate environment, they will start applying the policy, which is, for example, to say, hey, Facebook is not to be used in the workspace. You can use Facebook app only when you're in the cafeteria. Okay, that when you're sitting inside the corporate workspace, only certain apps are going to be visible, and a view of the apps that is going to be visible is going to be determined by the enterprise policy. Okay, so these things are available today. The only problem is that, so this is a solution for this BYOD problem, right? I mean, not problem, but this phenomenon of BYOD. So the employees are given a mobile device and there's a secure software stack, and enterprise policies, as I said, are going to be pushed to this device when the employee device changes the persona. That is, you walk from personal setting on the device to work setting, which happens, let's say, when you walk in the door and then you use your phone to swipe in to allow the door to open. Okay. So the only problem is that this enterprise software stack that is installed on this guest device, the enterprise must actually trust this software stack. And for the most part, that's okay. That's a reasonable assumption, except when the guest is malicious and can modify the software stack. So a sufficiently determined adversary can bypass this defense. Okay. And guest devices are in fact under the control of possibly malicious end users. Think about it, right? The enterprise wants to control the end users. It is installing its software stack on the end user's phone or mobile device. And in some sense, that software is sitting over there on the end user's device, who is the exact entity that the corporate entity wants to control. So kind of the trust model doesn't make sense. I want to control you. I'm going to install something on your phone and I'm saying, hey, that software is going to monitor you or is going to control your behavior. The point is that that phone is under your control. You can change that software in any way you want to, and there is no way for me to verify that that software is running there in a trustworthy way. Now there's a solution to this, right? And the solution that we have already studied in class, which is attestation. If I have some way of attesting the software that's running on your phone, I have some root of trust on your phone, then I can start building trust. And that's exactly what the ARM trust zone is, right? It's a root of trust on the phone via which the enterprise, the corporate entity can actually ensure that the software that they installed on your phone is actually running in a trustworthy way. But ARM TrustZone goes much further than that. It provides other features. We will see that now. Okay, so this work that I'm going to talk about today, I'm actually going to define a new notion, right? I'm going to define a notion of what's called a restricted space. So a restricted space, you can think about it as a location that is owned by a host, where guest devices must follow the host usage policies. Okay, so whenever you come into a restricted space and the guest device, maybe you walk in with your phone, you're a guest, and I'm the host of, let's say, the exam room, you must follow the rules that I set. Now, we have also extended this to drones in my lab, where we talk about restricted airspaces. Okay, so whenever a drone walks into, let's say, the IISc campus, the IISc security office may have certain rules for how the drone must operate inside this airspace. And as long as it conforms to that, we are going to allow the drone inside. Believe me, this is not really far from reality. India's drone policy is called Digital Sky. Okay, it's been proposed December 2019. It came in the first draft of Digital Sky came into effect. This is actually a reality today, right? The drones, they have so-called red zones that are there that the government decides. For example, army facilities and the airports and so on are marked as red zones, and drones must not fly into those red zones, right? And there's a digital way by which the air traffic control can actually enforce this. Sorry? Yeah, somebody's got a phone call, I guess. Somebody's not muted, so please go on mute. Okay. All right. So the guest device, what we want over here is for us to develop a facility by which the guest device can prove policy compliance to restricted space hosts. And I'm going to show you one particular low-level API that reduces the size of the trusted computing based on these guest devices. Okay. Oops. Okay. So let me just skip these key technical challenges and actually move on to the work. So the threat model is that of trusted hardware on these guest devices. So I'm going to assume that every end device, the guest device, is actually equipped with ARM TrustZone. And for things like drones, this is becoming a requirement. If you want to buy a drone and register it with the aviation authority, the hardware must be compliant with what the registration with what the aviation authority is saying. Think about it, right? Today, vehicles that are being sold have to comply with BS6 regulations for emission standards and so on. So just like that, you can imagine that there will be standards like this that come for mobile devices and drones. If you want to use them in our country, then you have to conform to these particular standards. Okay, and we will think about hosts and guests as being mutually distrusting. So the host do not have to trust the end user or the guest device, and the guest also does not trust what the host has to say, and we will still ensure policy compliance. And Of course, we are going to talk about guest devices that are being used overtly, no covert use. That's too hard a problem. Okay, so this is the overall way in which this solution is going to work. I'm going to describe like the overall operation. The overall operation is going to give rise to a wish list of things that we would like the devices to do, and we will see how you can realize this wish list using the TrustZone. Okay. So may I just ask everybody in class to check if they're on mute? I'm getting some static, which I typically don't get if everybody is on mute. So please make sure you're on mute. Okay, so you're an employee, you're walking into a corporate space. That's the assumption here. We'll call that the restricted space. So when you walk in from the public space to your restricted space, your device has various peripherals turned on. I'm showing over here Wi-Fi, Bluetooth, and 4G. Okay. Now when you walk in with those things, but now the restricted space is going to have some restrictions that they want on it. But this is called a check-in process. Okay, so the check-in process is when the ARM Trust Zones facilities are going to be put to use. Okay, so when you check in, there are going to be 4 steps that are going to be followed. The first thing is that of mutual authentication. So the host will assume it has some sort of a policy server which determines what the usage policy of the peripherals on the device is going to be. And the host policy server also knows the identity of the various devices, right? So you've pre-declared the devices and it knows exactly which device belongs to whom. So there is a mutual authentication step. This is not too different from TLS handshake. Okay, so that's the first step. So the second step in this particular solution that I'm going to talk about is that the host is actually going to analyze the device to figure out what peripherals are actually running on the device so that it can then determine what to ask to be turned off. So over here in this solution, in this paper, that analysis takes the form of actually device memory analysis. So the host policy server is going to request the actual physical memory snapshot from the device, which can compromise privacy too, but I will talk about that later. And it requests this device memory in the terms of like some address ranges. Okay, kernel memory ranges and so on can be requested by this policy server. And so because this is a big violation of privacy, right? I mean, the guest does not, if it gives up this memory, the host can actually figure out, maybe like the values of cookies, passwords, and so on. So you cannot just give arbitrary addresses. So we have got a vetting service in place where the host can talk to its own trusted server to make sure that the request is actually okay. So, and that it does not violate the privacy of the guest. So if the guest vetting service says that this is okay to proceed, at that point the device goes back and then sends a snapshot of its memory at that given point in time to the host policy server. I'm going to tell you how to implement every one of these steps. Okay, and then the host policy server sort of analyzes this memory and then sends updates. I will tell you what these updates are, but very briefly, the updates are basically updates to the device drivers of these various peripherals so that the peripheral is disabled from the kernel up. Okay, there is no way you can even turn on the device even if you want to, because the device driver is going to be disabled from the firmware up. And that's how you disable these things. Okay, and then again, these requested updates, you do not have to trust it. You, the guest, do not have to trust it. The guest vetting service will tell you whether the updates are trustworthy or not. When you apply the memory updates, then the various peripherals are disabled in accordance with the host policy. Okay, the host policy in this case, maybe it says, okay, Wi-Fi is okay. You can connect to only my access points so that I can actually monitor the traffic, but everything else that I don't control, you're going to stop. Okay, Bluetooth, no. 3G, 4G, no. Camera, no. Okay, so and all of those things are encoded in these memory updates. And when you apply the memory updates, automatically these policies are going to be enforced. And so at any given point during the stay of this mobile device in this host policy server, the policy server can request proof of compliance. Okay, and the proof of compliance, the device will have to just send. All it sends is that it sends a snapshot of its current memory, which will basically be the memory with the updates applied. And this we'll call a verification token. We will see over here an application of the HMAC technology. okay, that we studied in class. Okay, that's the overall idea, and that's the proof, because now the host policy server, if it sees that its updates have been applied and they have not been tampered with, that's proof that the device is still in compliance. Okay, when you check out, it's as simple as reverting the changes. Just apply the original snapshot of memory and everything else works as before, right? When you walk out of the building. Okay, so the whole point here is you're applying memory updates. So how do you ensure that the device is not rebooted when you're inside the restricted space? Because that tends to undo everything. I will tell you all of that. We have got solutions for all of that also. Okay, so how can the host trust the guest to apply the policy? Over here, you see that the policy is actually being applied on the phone by the phone itself. So how does the host ensure that all guests have applied the policy? Well, over here, we are going to leverage the ARM TrustZone for that. Okay. Second question is, why are we using memory snapshots and updates? Well, the reason is because a very powerful low-level API that allows you to reduce the amount of trusted code that the host needs to trust on the end user guest device. Okay, and then I'll also tell you about how this vetting services ensures the privacy of the guest, and I'll also show you, how the guest can't simply reboot the device to undo the changes, because they're all memory changes. They can be undone by simply rebooting. I'll show you how we prevent that. There's a special protocol for that called REM suspect. Okay, so now let me tell you about the ARM TrustZone, right, which is the centerpiece of all of this. So the ARM TrustZone, it's a trusted technology, just like the TPM and SGX and so on. It is in the chip itself, but unlike the TPM and the SGX, this provides a very unique capability. Okay, so what it does is that it splits the execution into two modes called a secure world and a normal world. So you can transition between the two worlds using a special instruction called the SMC, or the secure monitor call. Okay, but the idea is that the normal world is the world in which you typically reside, right? All your apps sit in the normal world. That's where you do your day-to-day operations. But there's a secure world that the normal world can call into from time to time that's protected by the hardware. And I will tell you exactly how it's protected. Okay. So you can split the execution mode into normal world and secure world. So the secure world offers a number of features. Okay, it offers the ability to securely boot the device. So secure boot is exactly what we studied in our TPM attestation lecture, where the secure boot protocol ensures that the device has not been tampered with. So if, for example, you change the operating system image of the operating system on your phone, the secure boot process will detect that and refuse to boot your phone. Okay. The secure world can also store public and private keys, and it can store them securely. So the private key is not made available to the normal world. Okay. And there is a partitioning of memory that's possible, in the sense that the secure world can access its own physical memory as well as the physical memory of the normal world. But the normal world is unable to access the secure world memory. So you partition the physical memory and you devote a partition to the secure world, so that the normal world cannot access the secure world memory even if it wants to. There's no way in which it can even physically address that memory. That protection, this partitioning and this protection is provided by the hardware, okay, by the memory controller itself. All right. So these are the features of the ARM TrustZone. And in fact, the secure world, it turns out to be a full-fledged execution environment, just like the normal world, in the sense that inside the secure world, you can boot a traditional operating system. You can, in fact, even run Android if you wish, right? It's a very expressive sort of execution environment. And the natural comparison that comes to mind when you think about SGX is this secure world similar to enclaves? And the answer is no, because unlike enclaves, where the execution is very restricted, you can't execute things like system calls and so on. The secure world is a fully separate partition in which you can run a complete operating system. So it's much closer in spirit, the secure world and normal world, to the notion of virtualization than it is to enclaves. So you can think about the normal world and the secure world as being two different virtual machines that are running side by side. And you can actually go from here to here and then switch back over here um, um, for services, except that over here, the normal world and the normal world can rely on the secure world to provide services. So for example, you can have a payment app that is tied to the secure world, and the normal world can access that payment app via API calls. There's also other features of the secure world that I didn't tell you. So for example, you can bind partitions to peripherals to the secure world. You can say, look, the camera is only usable from the secure world. So if you want to use the camera, the corresponding app to use the camera must reside in the secure world. Otherwise, the camera is not accessible. So all of those things are possible using the TrustZone. So what we do in this TrustZone, in this setting, as I said, the secure world is highly programmable. We implement all of this functionality that I spoke about, this notion of authentication, the normal world analysis, normal world updates, these memory updates, and the verification tokens that I spoke about are implemented within the secure world. And obviously, this is trusted software that needs to be tested. So let me tell you how all of these things are implemented. Okay. So mutual authentication. So the first time you walk in with your phone into your enterprise setting, what happens is that the host policy server in the secure world need to mutually authenticate. So what happens in a TLS mutual authentication? If you think back to TLS mutual authentication, there is a handshake with you and the other party at the other end of the TLS tunnel verify each other's public keys, and you establish a symmetric key for communication. Okay, that's what TLS does. Exactly the same thing happens over here, and we'll assume that the secret key KS is established at the end of this mutual authentication phase. Okay, so the thing is that this KS is known to the enterprise server, but on the phone side, this secret key KS is stored in the secure world. So it's protected from the normal world where all of the untrusted applications and so on sit. Okay, so it's going to sit inside uh, uh, the secure world, and no applications on the phone can even access this KS unless you're the secure world, which in some sense is trusted uh, by this hardware root of trust, ARM TrustZone that's sitting on the phone. Okay, so it's a simplified TLSSSL handshake, and the public and the private keys of the host and the guest, the public keys are verified against a certifying authority, and they negotiate this KS, and the KS is sent by the host to the guest encrypted under the guest's public key, which obviously the guest can decrypt and then store within the secure world after obviously verifying each other's public key signatures. Okay, so that's the first step. So the next step is that the host policy server sends this request to, let's say, access device memory. So it wants to know what device drivers are installed. That's how you figure out what peripherals are there. Every peripheral on the device must have a corresponding device driver within the operating system. So if you request a snapshot of the kernel, by analyzing that snapshot, you know exactly what peripherals are installed on the phone. No peripheral works without a device driver. Okay, so the device memory can be sent over to the host policy server, and of course it has to be integrity protected. So the device memory has to be sent by the secure world, because the secure world is the only one that's trustworthy on this device. So what happens is that the secure world, it reads the normal world memory, the normal world kernel memory with the addresses. It reads it. If you trust the normal world to read it, obviously the normal world can send a snapshot that is different from what is running on the actual phone. So the snapshot has to be obtained by the secure world, and the secure world basically sends the snapshot over to the host policy server. Now you can choose to encrypt the snapshot if you wish, but at the very least you want to integrity protect this, because all networking on this phone is controlled by the normal world, and you don't want the packets to be corrupted in the process of sending it. Okay, so what you can do is you can just add a MAC or an HMAC or something like that to the end of the transmission, so the host can ensure that the secure world, that the snapshot that is sent by the secure world has reached the host uncorrupted. Okay. So then the host policy server does an analysis of the memory snapshot. What kind of analysis? Well, we studied in this class, we studied the OSCK paper for rootkit analysis. Well, very similar to that, right? What did the OSCK paper do? Well, it analyzed memory snapshots of a virtual machine. Exactly the same way over here, you can actually analyze the snapshot of this phone's memory for the presence of rootkits. You can check what peripherals are installed, where in the memory the device drivers are installed, and so on. So you'll know the exact location of these device drivers. You, the host, I mean. And then what happens is that, okay, so why should you look for rootkits? Well, the reason you should look for rootkits is that if you don't look for rootkits and you just send updates to the device, and the device just applies those updates, the rootkit, if it's installed on the normal world, can just undo those things. Okay, undo those updates. So the rootkit will undo the host changes, and then all the peripherals will then become enabled once again. So the host policy will not be enforced. Okay, that's the idea. Okay, so the analysis of the normal world snapshot, you can actually check for, whether the code that is over there belongs to a whitelist, whether the data structures or the memory that are there in the kernel, they are conforming to some invariants, the kind of invariants we spoke about when we talked about the rootkit lecture and so on. Okay, so that's what the host can do with a memory snapshot. And at the same time, the guest can also vet the requests. So the vetting server ensures that the host's requests for memory do not compromise the privacy of the guest device. So one easy way to do this is that the host is only allowed to request the guest device's kernel memory, not actually the memory of user space applications. So things that are in the application memory are protected from the host view. Okay, so at this point, after analysis, the host can actually send a bunch of memory updates to, let's say, uninstall device drivers. So, and the secure world actually updates the normal world memory. It receives these updates and it can just write to that memory, thereby updating the normal world, thereby uninstalling the device driver. So what kind of updates? Well, here is how things work, right? So whenever you have a device driver in the operating system, it so turns out that all operating systems are programmed this way, that there is a bunch of generic hooks inside the operating system kernel. These hooks are implemented as function pointers, via which the operating system talks to the device drivers. Okay, because the operating system kernel itself is written a very generic way. It's not written with any particular peripheral in mind. Therefore, the interface to the devices are very generic. They're implemented as function pointers. And the device driver itself implements various functions and then links them up with these function pointers so that the operating system can talk to a generic device and those requests get translated to specific device functions via these function pointers. So this is how operating system kernels are implemented and how device drivers are implemented. Whenever you install a new device driver, it registers itself by just changing a function pointer to its own corresponding function. So all you have to do in this way to uninstall a device driver is that you install a dummy driver, which basically does nothing. It does not actually communicate with the device, and then you hook it up to the operating system kernel. So if you introduce these dummy device drivers, you can actually disable peripherals on the device. This can be shown to work to disable various kinds of device from the operating system up, so that even if an application requests access to, let's say, the camera, and the operating system attempts to talk to the camera, it's talking to a dummy device driver, which does not turn on the camera at all. So you never read from the camera buffer or write to the camera buffer. So that's how you can disable a device from the operating system up. And these updates can just be encoded as the new device driver plus updates to the kernel function pointers. It's as simple as that to uninstall a peripheral from your phone. Okay, so it turns out that's actually incredibly effective way to disable various kinds of peripherals, right? So we tried this on at that time, an Nexus phone, as well as an experimental board. We were able to actually disable the camera, Wi-Fi, 3G, both voice and data, microphone, Bluetooth. All of these things can be disabled by just updating the device driver and changing the function pointers. Right over here, you can see the size of the update, which is basically, how many bytes need to be overwritten in the kernel to disable the corresponding peripheral. Is just a few hundred bytes. It's not even a huge update, right? To update the camera, for example, is around 200 bytes of data that you just overwrite. The camera is disabled. Okay, so it's incredibly effective way of turning off peripherals. Okay, even over here, the host might want to vet the update of the guest might want to update the vet the update of the host, because the host might actually be trying to install a rootkit. Remember, the guest and the host are usually distrusting, so the guest does not have to believe everything the host says, including the memory updates that it's providing. So the vetting policy over here is to ensure that the functionality of the device driver that is being installed, the dummy driver, is actually a subset in terms of functionality of the original device driver. If you can ensure this, then you can ensure that no new functionality at least is being installed into the device. And the way you can actually enforce this is by simply doing an ARM binary analysis on the updates that are being sent. If you do a binary analysis and see what instructions are being sent, you can ensure that the updates are strictly a subset, functionality wise, of the original device driver. Okay, so that's how you ensure safety. All right, and the proof of compliance is just the secure world fetches a snapshot of the normal world kernel at the places where the updates were applied and sends that snapshot, the latest snapshot, together with an HMAC with a key back to the host policy server. The policy server has to just ensure that the updates that it applied are still there, that they have not been undone. Okay, so that's the proof. Okay, so the secure world simply computes a fresh snapshot of all the normal world memory locations that were updated. So that is being denoted by this little array over here. You take a snapshot and you just hash it together with this key KS and then send it off to the host, who can then verify it. And the verification token, it will match if and only if the normal world has not maliciously attempted to modify these things. Otherwise, the HMAC will not match. Okay, and so that's the proof of compliance. All right, let me just briefly stop here. Any questions so far? Okay, so
Sir,
I encourage you. Yes, Shashak, yes, please go ahead.
Sir, of course, we need physical hardware support for this. Is that correct?
Yes.
Right?
Yes, ARM TrustZone is that physical hardware support. Yeah.
Yes, sir. It's a TPM module basically, right?
Well, it's much more than TPM, right? TPM
Yeah.
only provided secure boot, and secure boot is sort of there as part of ARM TrustZone, but it has other things, right? Like memory partitioning, the ability to bind peripherals to individual worlds, and the whole implementation of the secure world, normal world. So it's much more than the TPM. Just like the SGX also uses attestation, but it's much more than the simple TPM.
And
So these are,
yeah. And the OS doesn't need to be aware of this, right? The environment it is running in, just like the virtualizations, right?
I believe you're right. The normal world does not have to be aware of this, of the fact that it's running on top of the trust zone. Of course, if you want to make transitions into the secure world, those instructions have to be there. And so the applications at least have to be able to perform these secure world switches in order to be able to leverage that functionality. Yeah.
Okay. Yeah.
Okay. So it's a much richer version than just the TPM. The TPM was our starting point for the attestation protocols, and I told you then that I will be referring to attestation protocols over and over. And so you can see over here, for example, in the ARM TrustZone, we also use attestation as part of secure boot. But I didn't get into the details, exactly similar to what we spoke about in that lecture. So it's building blocks, one building on top of the other. Okay, so let's go back to the lecture. Okay, so one big problem is that, everything that we have done so far is in terms of memory updates. The only problem is that memory updates are ephemeral, right? So the guest device can simply reboot the phone or the device and then undo the memory updates, because when you reboot, the phone is going to erase the memory, and then when you reboot, you're going to get the snapshot of the OS after the reboot, right? None of the host updates will be there. So how do you protect against such attacks where the guest can just reboot the phone? So what we require is that the device, once it's checked in, the secure world is able to actually mediate all low battery and power off interrupts. Right? When you try to power off your phone, how does your phone get powered off? Well, you're pressing the power button. That's one way to power off your phone. But how does the power button work? The power button is just another peripheral that's installed on your phone, and the operating system is handling that interrupt. So all we'll require is that the power button interrupt be handled by the secure world, which is trusted. The other way that your phone can go off is low battery events, right? Which is that whenever the battery threshold crosses a particular level, there's an interrupt that's sent that to warn of low battery. And even over there, we'll assume that the secure world is going to take over. Of course, there can be another way to turn off your phone, which is you open the back cover and just you yank off the battery, in which case there is no time to even raise a low power interrupt. But of course, if you're going to be so determined, then at the time of checkout, it'll be there. And the fact that the updates are not there, and at that point you will be in trouble, right? So what we will require at least is that, if you're mediating all of these low battery and power off interrupts, then when these things happen, the secure world is going to checkpoint the device memory on disk. Okay, and upon power up, whenever you choose to power up the phone, you will restore the device memory from this checkpoint, so that the host's updates to memory are actually checkpointed and restored from the checkpoint, so you never lose those updates. Okay, so the device checkpoint is actually stored on disk. The only problem is that if you store the checkpoint on disk, it is going to be readable by the end user, right? Because at the end of the day, you can just retrieve the disk and read the checkpoint. And the session key that is stored in that checkpoint, the checkpoint stores everything, right? Including the session key KS that's in the secure world. And the problem is that if the session key becomes available to the attacker can do anything and impersonate the secure world. Okay, so the session key should not be stored in the clear. And if it is stored in the clear, then the attacker, who is the end user, can then impersonate the secure world. So how do we protect against this? So that's where we talk about this new protocol called REM suspend. I will tell you what that is. So it turns out that every device, ARM TrustZone device, according to its specification, it can allow the device to have a device specific key. We'll call that KDEV. Okay. So every device will have its own device specific key called KDEV. That's actually part of the hardware specification itself. And this KDEV is only accessible from the secure world. It's not accessible from the normal world. So what you can do is that this KDEV can be used to encrypt this key KS in the checkpoints, and then the key KS is stored in encrypted form in the checkpoint. When the device is powered on again, the secure world is just using this device specific key KDEV to restore this KS back in memory. So this is how you protect the confidentiality of KS, even when it's stored on the disk in this checkpoint phase. So this is how it works. So when you're going to power it off, see over here, what you see is a checkpoint. The memory snapshot is going to be stored on device storage. Whole thing is going to be integrity protected with KS, probably using a HMAC. And the key KS itself is also going to be stored securely, itself encrypted under KDEV, so that the value of KS is never available in the clear in the guest device storage. When you boot up, the secure world will use KDEV that only it can access to retrieve KS, integrity check the snapshot that's stored, and then restore the phone back to its normal state. Okay, so let me just go over some evaluation details, right? I mean, we took all of these great pains to ensure that the way that you update the phone by or make the peripherals inaccessible is using memory update. So you might ask, is that the right API? Are there better ways to do this? And so it turns out that at least if you if you use this memory update based technology to disable peripherals, the size of the trusted computing base, which is the amount of code that's running inside the secure world, can be brought down to a few thousand lines, right? In around 6 to 7,000 lines of code, you can implement all of the functionality that I told you: normal world, snapshotting, normal world, memory update, secure boot. All of these things can be implemented in just around 6,000 lines of code inside the secure world, and that is all that needs to be verified during the secure boot process and sent over to the host server, and that serves to actually build a trusted code base on the phone. Incidentally, we use the embed TLS library to build all of this functionality. The SHA-1, HMAC, X509 certificates, all of these things we implemented inside the secure world. We use the components of the embed TLS library that you guys are currently working on as part of your project. Of course, an older version to implement all of this crypto functionality. Okay, and we did a whole bunch of experiments to check whether these memory updates actually affect the stability of the app. You can think, maybe an app is actually using the camera, and what happens to the app if the camera is disabled. And so let me just focus on one, the camera over here. We took 5 applications and then we checked what happened when the application tries to access the camera, and actually you get an error. Which applications are well programmed, that are well programmed can actually deal with. So if the camera is spoiled, the application needs to be able to have error cases to deal with that, and that is we were able to gracefully deal with that error. Likewise, 3G voice, you can see you're unable to place a call. So this is when you update the memory and start the app. You might ask, what happens if you have got an app that's already running and then you update the memory? You get similar errors, right? So for example, the Android Cam application, when you do an update when the app is running, you just get a blank screen, right? With the camera, you're not able to see the actual images. Okay, so there's much more evaluation in the paper, including performance evaluation. It's around 4 years old, so the paper is not too dated. But what I've shown you is actually a systematic method to regulate devices and ensure responsible use. And I've shown you how you are able to accomplish it with a small size TCB. And I also showed you, how the ARM TrustZone plays a crucial role. Now, I'll actually encourage you. So this is work that came out of my own group a few years ago. Let me just show you some more recent work that came out of my own lab, which is along similar lines. That continues this theme of work. So if you're interested, I encourage you to actually go and look at this paper called Pre-requisites, which applies a very similar method, but without memory updates. So it's a much simpler methodology to the problem of delivery drones. We've got a fun video also. So, and if you're interested, you can actually talk to Rakesh. He is there in my lab, and we have applied this to drones, and actually we have applied it in the context of India's digital sky. So we have proposed an architecture whereby you can control drones, and we have shown how you can integrate this with India's digital sky API. So the hope is that you can achieve privacy in this era of drones once delivery drones become a reality in India's airspaces. Okay, so if you're interested, I encourage you to go read that paper. If at least if not for the purpose of the course, just for the sake of curiosity, because I'm sure you can all relate to e-commerce based deliveries, food deliveries, and so on that are happening today. you can relate to these things happening via drones probably in the near future, 4 to 5 years from now. People are very seriously talking about this for end user, at least the last mile delivery. So we have got a solution for the privacy problems that will arise in this space. So I encourage you to go and take a look. So with that, I have nothing more to say as far as the class material is concerned. Let me just stop the recording. I can take some quick questions and then we'll call it a day for today. Yeah, any